Hello again. Third lesson on differentiation for Year 13 Edexcel A-Level. So you've had a look at differentiating sines and cosines, exponentials and natural logs. And now we're going to have a look at something called the chain rule, which is one of the most important results of all of A-Level maths, which allows us to differentiate harder functions where we have a function of a function within another function, if you will. I'll explain as we go through, but before we get to that point, let's have a few warm-up questions. So here they are. 3 today in total. Well, I suppose 3 is in parts A and B, so 4 essentially, I suppose. So try these now. Press play when you're ready to see the solutions after pausing when you're attempting them. Then hopefully your answers will be absolutely fine, and if not, I'll show you where you may have gone wrong. Okay, so assuming you've had a go at these questions, let's have a look now together at warm-up question 1. So for warm-up question 1, we have to differentiate y, given that y is ln x cubed plus 6e to the minus 2x. So first of all, I'm going to rewrite y as 3 ln x, just bringing this power of x to the front, which we're allowed to do, plus 6e to the minus 2x. We can now differentiate both sides, so dy by dx. The natural log of x differentiates to 1 over x, so this becomes 3 times 1 over x, which is 3 then x, and this constant here in the power of e drops to the front, so we have 6 multiplied by the minus 2, which gives us minus 12, and then we have e to the minus 2x because the power stays as it is. And so that's what we get when we differentiate it. So that's question 1 done. Warm-up question 2. Question 2, again we have y, which is 5 over 2 e to the minus 3x plus 3. We need to find the gradient function dy by dx, where x is equal to 3. So first all we need to do is to differentiate y with respect to x. So dy by dx will be 5 over 2 multiplied by, this constant comes to the front, so we have minus 3 e to the minus 3x, and of course if we differentiate the constant 3, that just disappears entirely. So 5 over 2 multiplied by minus 3 gives us minus 15 over 2, or minus 7.5 e to the minus 3x. So when x is equal to 3, don't know, I was going to say minus 3. When x is equal to 3, dy by dx at the point where x is equal to 3 is going to be minus 15 over 2 e to the minus 3 times 3, which of course is minus 9. So that's a very, very shallow gradient. The graph is almost flat at that point, essentially. So use Desmos if you don't believe me. So the gradient when x is equal to 3 is minus 7.5 e to the minus 9, which is very, very small and negative. Question 3, we have a particle that moves along a straight line from point x to point y with constant acceleration. Key point here, it says constant acceleration, therefore we can use the SUVAT formulae. The distance from x to y is 104 meters. The particle takes 8 seconds to move from x to y, and the speed of the particle, it should say at y, the speed of the particle at y is 18 meters per second. So first of all, we need to find the speed of a particle at point x. So because it's constant acceleration, we can use a SUVAT formulae, which are here, and then we can decide which one we need to use. So let's first of all fill in out of SUVAT what we know. So S, U, V, A and T. So we're told that the distance from x to y is 104 meters. So that is the displacement, so we know the displacement is 104. So yes, we know S is 104. Particle takes 8 seconds to go from x to y. That tells us the time elapsed is 8 seconds, so we can fill in the time. And the speed of a particle at y, it should say, like I've said, is 18 meters per second. So the final velocity is 18. Now for part A, we want to find the speed of a particle at point x, which is the initial velocity. So I'm going to put a question mark there. And for now, we don't know A, we don't want to know A, so we can just leave A alone. So we need one of these SUVAT formulae, which does not involve A, because we're not interested in A. And so the one we can use here, which doesn't need A, doesn't depend on A, is SUVAT equation 2. S equals a half, brackets U plus V times T. So let's use this one. So using S equals a half u plus v times t, we can then substitute in the values and then work out what u would have to be. So S is 104, so 104 equals a half. U plus V, I don't know U, so I'm going to leave it as letter U. V is 18, of course, because it says here V is 18, as in the question. And the time elapsed, the time elapsed is, of course, 8 seconds. So T is 8. So we just need to rearrange this, really, and then it'll drop out. So 104. A half times 8 is 4, so that's 4 times u plus 18. If we now divide both sides by 4, we can work out what u plus 18 would have to be. 104 divided by 4, that gives us 26. So 26 equals u plus 18. Therefore, when we subtract 18 from both sides of this equation, we see that u is 26 minus 18, which is 8 meters per second. So u is 8 meters per second. We can now think about what a is. So we can fill in that we know u now. We know u is 8, so we can say goodbye to the question mark and fill in with what it actually is. Knowledge is power. We know more knowledge, so we can add it down with pride. So next, b. We need to find the acceleration of the particle. Now, because we know everything apart from a, we can use whichever formulae we want, as long as it involves a, of course. I think the most obvious one is just here, first equation, because a is a subject, and we've worked out what u is from part a. So the acceleration is the change in velocity, v minus u over t. The final velocity is 18. The initial velocity was 8, so 18 take away 8 divided by t, which is 8. So that's 10 over 8. So 10 divided by 8, let's see what that gives us. 10 divided by 8 gives 1.25 meters per second squared. So that's the warm-up done. So now let's have a look at the main part of today's lesson, which is, of course, the chain rule. So the chain rule. So what is it? Let's just talk this through. So, well, the chain rule is a powerful mathematical tool that enables us to differentiate more complicated functions of x. If y could be written as a function of a function, where y is a function of another function u of x, so that y is a function of u, where u itself is a function of x, we can now differentiate this using this device called the chain rule. So dy by dx equals dy by du, y differentiated with respect to the variable u, then multiplied by du by dx, which means the function u differentiated with respect to the variable x. So although these are limits and don't work the same as normal fractions from GCSE and before, it does look like the u on the bottom and top cancels to give you dy by dx. So although that's not a robust way of looking at it mathematically at this level, we can get away with that as a little hack to let us make it easier to remember the formula. So just think of it, although it's not strictly true, that the u's cancel there and there. That's how you get dy by dx. So, in function notation, if y equals a function f of another function u of x, then f of u of x all primed, all of this differentiated, is actually f primed, so differentiated f with respect to u of x, then multiply that by du by dx. So as you can see, this notation is quite clunky. It doesn't look as nice as this one. So for that reason, partially, this dy by dx, dy by du times du by dx looks much neater. That's one of the main reasons why this chain rule is given in this form. And that's why I'll be using this mainly for this chapter and generally throughout as well. This is just my preferred way of working it. I'll also link you to a proof of the chain rule in the description of the video as well, in case you need to see it being proven to help your understanding. But don't worry, you should not need to know how to prove the chain rule in your A-level examination. You do need to know though how to use the chain rule. So let's have a look at this in a bit more depth. So, first of all, let's have a look at a worked example showing that this chain rule actually works, and also we can have a first look at how it works. So let's imagine that we've got a function y, which is 2x to the power 4 minus 3 all squared. So part A, what we're going to do, we're going to see that the chain rule works by differentiating as standard, and then we'll use the chain rule and compare. So first of all, let's take this y, expand out the brackets, and then differentiate it as normal. So if y is 2x to the power 4 minus 3 all squared, then if I square out these brackets, 2x4 all squared would be 4x to the 8. We then take the product of this and double it, so 2x4 multiplied by minus 3 gives us minus 6x to the power 4. Double that gives us minus 12x to the 4. Finally square the last term, minus 3 multiplied by minus 3 gives us plus 9. Therefore, as usual, dy by dx, bring the 8 to the front, multiply it by the constant, so we get 32x to the 7. Bring this 4 to the front and multiply it by the minus 12, gives us minus 48x to the 3, and the 9 is a constant, so it just vanishes. So dy by dx is 32x to the 7 minus 48x cubed. Now for part B, we're going to use this chain rule. So let u equal 2x to the power 4 minus 3. So let's say that u is 2x to the power 4 minus 3. So that y equals u squared. Because obviously y is this thing here squared, and we're calling this u. So y is u squared. So based on these two things here, we can differentiate u, first of all, with respect to x, du by dx. Bring the 4 to the front, times it by the 2, gives us 8. And take 1 off the power of x, gives 8x cubed. The minus 3, of course, disappears. And if y is u squared, if we differentiate y with respect to u, bring the power to the front, as usual, drop 1 from the power, so it becomes 2u to the 1, which of course is just 2u. So that's part 1 done. And part 2 of this question asks us to find an expression in terms of x and u for dy by du and then du by dx. So dy by du is 2u, and du by dx is 8x cubed. So when we multiply these two together, dy by du multiplied by du by dx, this is going to give us 2u multiplied by 8x cubed. So that's because du by dx was 8x cubed, and of course dy by du is 2u. So 2 multiplied by 8 gives us 16. X cubed multiplied by u, or u times x cubed, is just u x cubed. However, we want to then resubstitute so that it's all in terms of x. So we said that u was 2x to the power 4 minus 3. So if I just put that back in fact, I'll put the x cubed first. So I'll put 16x cubed, brackets, 2x to the power 4 minus 3. Part 3, expand your expression from part 2. So I'm going to expand this out and compare with this underlined from A. So 1, 2, 3. If I expand, this 16 times 2 is 32. X cubed times x to the 4 is x to the 7. 16 multiplied by minus 3 is minus 48, so that gives us minus 48x cubed. So that's what dy by du times du by dx is, which of course is dy by dx, and gives us the same as what we had from part A. So therefore dy by du multiplied by du by dx does give us dy by dx as we saw from part A. So to conclude this question, part 3, what do you notice? The results are the same. So therefore, the result is the same. Results are consistent, we could say. In other words, in plain English, the chain rule works. So now we know it works, let's apply it with some more worked examples. So, first, worked example proper. So given that y equals sine cubed x, find dy by dx using the chain rule. So what we can say here, we can just say y is u cubed where u is just sine x. So if y is u cubed, if I differentiate y with respect to u, that gives me 3u squared. And over here, if I differentiate u with respect to x, sine differentiates to cos. So and therefore, dy by dx, which is dy by du multiplied by du by dx. Dy by du, of course, was 3u squared, and du by dx was cos x. So dy by du, 3u squared, multiplied by cosine of x. But if you put it all back in terms of x, u, we said, was sine x, so 3u squared is the same as 3 sine squared x, multiplied by cosine of x. So normally what we do, we choose u such that it makes the expression we're trying to differentiate much easier. U cubed looks much neater than sine cubed x. This is a process you'll see once we go through more examples. Worked example 2. Again, this looks quite ugly, so what could we choose u to be to make this look much neater? So what we could say, we could let u equal 5x squared plus 1. So let u equals 5x squared plus 1. Therefore, if we set u to be that, then y is the square root of u, which in power form is u to the power half. So u is obviously 5x squared plus 1, so we can do du by dx, which differentiates to 10x, and differentiating y with respect to u, but half comes to the front, and we subtract 1 from the power. So there's our du by dx, and here's our dy by du. So from these two bits here, we can say therefore dy by dx, which is dy by du multiplied by du by dx, is therefore going to be a half u to the minus a half multiplied by 10x. So a half multiplied by 10, of course, is 5, so this gives us 5x, pardon me, and then u to the minus a half is the same as 1 over the square root of u. So this is a square root of u, it's going to be on over, and u, of course, was 5x squared plus 1. So we just replace u with what u actually was, and that's our expression for dy by dx. So again, like before, we work out dy by du, like we did, then we multiply that by du by dx to give us this result here. So, moving forward, there is a special case we need to know about as well. So the following particular case of chain rule is very useful for differentiating functions that are not in the form y equals f of x. It's a reciprocal form of the chain rule, and it goes like this. It's very simple. Dy by dx is the reciprocal of dx over dy. So in other words, it's a similar looking thing to GCSE fractions, although we can't actually say they work in the same way. These are limits, not fractions as such. But again, the link works to make the memory easier for us. So 1 over dx over dy is the same as dy by dx. So let's see how this can be useful. So in this example here, we need to find dy by dx at the point 6, 1 on the curve with equation 5y squared plus y equals x. So the first thing I'm going to choose to do, I'm going to write this with x as a subject. So if I put x first, so x equals 5y squared plus y. That's what x is. I'm now going to differentiate x with respect to y. So the power of y will come to the front, just as we're used to doing this with powers of x. But because we're differentiating in terms of y, it's now these powers of y that will change. So 5 multiplied by 2 gives us 10, y squared becomes just 1y, and y differentiates to just 1. So therefore, dy by dx will be 1 over 10y plus 1. Now, we need to find out the value of a gradient of a point 6,1. So if we just sub in the point where y is 1, dy by dx, when y is equal to 1, is simply 1 over 10 times 1 plus 1, which is 1/11th. Therefore, the gradient when x is 6 and y is 1 is 1/11th. We can also use the fact now that dy by dx is 1 over dx over dy, along with the property that if y is e to the x, the exponential function is its own derivative. We can now prove, finally, that the derivative of e to the x is ln x. Sorry, the derivative of ln x is 1 over x, I mean to say. So let's have a look at this result and proving it. So now let's prove the derivative of ln x. So step A. We're going to let x be a function of y, such x equals ey. So we're going to take natural logs of both sides of that equation, and we're going to show that y equals ln x. So what we're going to do here, just start by saying x equals ey, then take logs of both sides. So ln of x will equal ln of e to the y. If we take the natural log of e to the y, that y will come to the front. So we have y ln e, but log base e of e is just 1. So ln e is 1, so y multiplied by 1 just gives us y. So therefore ln x equals y. So we can use this now for part B. We need to find dx by dy and then find dy by dx. In fact, I'm going to just use this first line here, that x equals e to the y. So if x is e to the y, we can differentiate both sides with respect to y. So dx by dy, if I differentiate this with respect to y, the exponential function is its own derivative. So if I differentiate e to the y with respect to y, I'll still get e to the y. So therefore, if this is dx by dy, dy by dx will be the reciprocal of that, which is therefore 1 over e to the y. Then for part C, it says prove therefore that if I differentiate the natural log of x, it's 1 over x, by using that y is ln of x and x equals e to the y. So from this result here, we can resubstitute that x equals e to the y. So if I sub in that x equals e to the y, then this here, dy by dx, which is 1 over e to the y, becomes 1 over x. So therefore, dy by dx equals 1 over e to the y, but that's the same as 1 over x. So putting it all together, we've got our result. So we said that y was ln x, then we have dy by dx is 1 over x. So therefore, if y is ln of x, dy by dx is 1 over x, and we've proven it. Now, sometimes we have to differentiate some beasts, compound chains, where it's several uses of the chain rule in one. So sometimes a question will ask you to use repeated iterations of a chain rule. So here's a harder example. So let's differentiate dy by dx if ln y is sine cubed 3x plus 4. First of all, this isn't the form y equals. So what I can do first of all is exponentiate both sides. So e to the power of lny is going to be the same as e to the power of sine cubed 3x plus 4. Now, that isn't just an x, it's not even a 3x, it's a function within an exponential. This is quite complicated indeed. So what I'm going to do here, I'm going to just call this equals e to the big U. We can choose whatever variable we want, but I'm going to choose e to the big U, where big U is sine cubed 3x plus 4. Then we know, using the chain rule, that dy by dx, and of course e to the lny, that's the same as y, of course. Dy by dx is dy differentiate with respect to big U times du by dx. So if y is e to the u, if I differentiate y with respect to big U, that stays as e to the u times du by dx, which we can't yet work out because u is quite complicated. So let's look inside u. So u, big U, is sine cubed 3x plus 4, and I'm going to call this now, I'm going to call that equal to w cubed, where w is just the sine of 3x plus 4. So I need to split du by dx in terms of w as well, and in terms of differentiating in terms of x. So let's think about how I can get a chain from du by dx. So du by dx is the same as du by dw times by dw with respect to x. Let's put this in a little bubble here. So if u is w cubed, then differentiate that with respect to w, that's going to give us 3w squared. And then differentiating w with respect to x, if I differentiate sine of 3x plus 4, then that 3 will come to the front, and I just have 3 cos, because sine differentiates to cos. There'll be 3 lots of cos 3x plus 4. So that's how du by dx relates. So I split this bit of a chain into another chain involving another variable, another function, w. So du by dx is this thing here. So I've now got e to the big U multiplied by 3w squared multiplied by 3 cos 3x plus 4. So all this bit at the end is du by dx. So what was big U? Well, big U is just all of this sine cubed 3x plus 4. So big U is just all of this stuff here. So if I now resubstitute this back in, 3 times 3 gives us 9. W was sine 3x plus 4. So w squared is sine squared 3x plus 4. Cos of 3x plus 4. Finally, multiplied by e to the big U, where big U is sine cubed 3x plus 4. So that's definitely a juicier example. They can be quite in-depth and involved, just like that one there. So that should give you a good grounding now to have some flight on your own and try some of these examples yourselves. So if you turn to page 239, exercise 9C, and attempt questions 1 to 5, then questions 10 to 13, that should stand you in good stead for knowing how to apply the chain rule to exam-style questions. Check your answers regularly. This is a huge skill to master, so take it seriously and ask for help if needed. I hope you found the video useful, keep working hard, and I hope to see you all very soon indeed. So from me, for now, goodbye and take care.